go. So you want to open your books to 811. What do exponential graphs look like? Okay, we're gonna do 1 through 5 together. So let me go to my slideshow. I made a slideshow for this. Hello, March. It is March 1st, if you didn't know that. You know, another thing that's happening this month is that the time is gonna change. You guys know what day that is gonna happen? Any ideas?
No, I have no clue.
I think it's March 14th, whatever that Sunday is, right? So, oh, didn't we say the end of the semester? Is it March, Reese, is it March 12th? Did somebody look that up? End of semester? It's March 12th, right? Friday, Saturday. So this would be Sunday. So I think those are the correct dates. We're gonna spring forward, right? On that day. So you lose an hour of sleep, but hey, that's okay. It's distance learning. So you get to roll out of bed, you know, whenever you want to. You don't even have to get out of your pajamas. So we're going to spring forward on March 14th in a couple weeks here. So that weekend after grades close for 3rd quarter, right? We will spring forward. So just a little note about that. Happy March, guys. It's March 1st. We're over with February. Let me go to the next slide here. Advanced slide. Okay, makes me want to use, it's making me use the controls. Okay, number 1 here. Let's investigate y equals b to the x. What do exponential graphs look like? Okay, so let's write this down for 8.1. My pen back, 8-1. So we have an exponential graph, y equals b to the x power, like this, right? What does this look like? Is this going to be a line, guys, if we graph this? Is that what an equation of a line looks like?
It'll be a line, just not a straight one.
All right. Okay. It's just not a straight line, right? It's actually gonna, when you throw an exponent, anytime you throw an exponent in there that's not a 1, what it does to the line is it curves the line. Okay. So when we throw an exponent that's not 1 in here, x can be anything. It could be, you know, x can be b to the 2nd, b to the 3rd, b to the 4th. We can throw all kinds of exponents in here. Okay, we're gonna explore, well, we'll see today. You already know that equations of the form y equals mx plus b represent the family of linear functions. That's what a line is, right? Y equals mx plus b. We've done a bunch of those first semester. Well, now we're moving on to harder stuff. So you know what effect changing the m and b, and we know what happens when we change m and b. We studied that all first semester. Today, we're going to study y equals b to the x. In chapter 5, you graphed several exponential functions. Okay, it talked about the bunny problem. You know, when bunnies have bunnies, they reproduce very quickly. So when they reproduce, they multiply, and then they really take off. So that's why you're not supposed to like just let bunnies free, because, and lots of other animals too, they will reproduce like crazy. Even cats, there's a problem with cats. So we try to get them fixed, right? So that they don't like just go crazy and take over. So, you have an exponential graph like this. The other problem we did was a bouncy problem. I think we skipped these problems, but last year we did them. We did the bouncy ball problem. Like if you take a bouncy ball, you drop it, right? It's gonna go lower, 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 lower. And so that graph is gonna go like this. It's gonna be not growing. It's gonna be decaying, but it's still an exponential. It's some y equals b to the x. And this is some y equals b to the x. So we're gonna explore this chapter. That's what this whole chapter is about. It's about exponential graphs, some y equals b to the x, okay? So each team member should write down 3 different numbers, use these teams. We're gonna do y equals 2 to the x. So go ahead and write that one down. Okay, I think we're all gonna do that one. So instead of each team member doing a different one. All right, so that's problem number 1. If you drew the graphs, awesome. I'm gonna clear this out and go to the next slide. Okay, investigating y equals b to the x, part 1. Each graph your team created in the previous problem probably looked different from others. How many different ways can the graph of the form y equals b to the x appear. Your task with your team, really it's going to be by yourself, try different values of b to find as many different looking graphs as possible. Stick to small values of b, for example, less than 10. Okay, so we want to go between 0 and 10. So we could write this down. So we want to make b between 0 and 10, or less than 10. So between 0 and 9, right? So it'd be like y equals 3 to the x, or y equals 4 to the x, or y equals 0.5 to the x. Okay, so numbers between 0 and 9. So you could write this down for number 2. We could, you're supposed to pick 3 values. So, you could write those down, or any other ones between 0 and 9 for number 2. Okay, so what you're going to do right now is you're not going to use this Desmos tool. You're going to use the Desmos that I linked in the classroom. Okay, so I'm going to get off of this and show you the Desmos that I linked in the classroom. Okay, the Desmos that's linked to the classroom. So you got to go back to the classroom and go to the classwork for today, A21. We're on assignment 21, 811. Okay, and click on this link right here, 811 intro. That's the Desmos activity. It'll take you straight to Desmos. It'll look like this, and you go ahead and type your name in. I'll be able to see on my Desmos account, where's my Desmos account, who is logged in. So go ahead and go there. I'm going to pause my video while we do this. So yeah, you want to click on slide number 1 and move the B back and forth. What happens when you change the base? So move the slider back and forth. What happens to the graph? And I can see this person's graph, okay? They have the slider at 6.1. So their equation is y equals 6.1 to the x power, okay? And if I go to the next person, this is the next slide. We're going to answer that. So after you slide this slider back and forth and see what happens to, watch what happens to the graph, then you're going to go to the next slide and you're going to answer this question. On the previous slide, you made changes to the b value in the equation y equals a times b to the x. What happened to the graph when b equaled 1? So make b equal 1, go back and make b equal 1, slide this over till b equals 1. Somebody did that. I'll pick a different person besides Pierre. I think this person did it. So let me go back on their slide. Can I go back to slide 1 right here? So if you pick b equals 1, the line turns out to be what? Straight line. The curve turns into a flat line, right? So go ahead and type that in slide number 2, right? When b equals 1, the line, what happens to the line? It makes a straight line, okay? And I want to not display all this person's answer. Somebody put me a message in the chat, so I'll look at that. Oh, good. Oh, that's so sweet. I'm glad that one of you will be volunteering at the homecoming this Friday. That makes me happy. And one of you put, yes, it is a flat line. Good job. Okay, now let's go on to slide 3 here. Investigate the effect of A in y equals a times 2 to the x power. Move the slider and see what happens. So make B2, okay, make your B2 and then slide the A slider. So let's see if I can, how can I, I'm trying to, so let's go over, oh no, I go back to the slider one. Maybe this person looks like they have it. So make B2, it should be a curve. And then your A slider, I don't see my A slider on here, but the A should be down here. Do you guys have a slider for A? Let's see. No. Where's the A slider? Oh, here's the A slider. It's on the third slide. So you have to go to the third slide and look what happens when we slide A around. Okay, whoa, what happened there? Okay, what made the graph go down when A is what?
negative.
That's right. When A is negative, the graph goes down. It flips it over basically. And then when A is positive and you make A bigger and bigger and bigger, what happens when you make it bigger and bigger and bigger? It's bigger and bigger and bigger.
It becomes steeper.
Yeah,
Its y-intercept changes.
Exactly. The y-intercept changes and it gets steeper. So that's what you're going to type. Good job, guys. So that's what you're going to type here in the last slide. Okay, and this lets me know that you're following along and that you logged in and you did the very short Desmos activity. So you want to type that in slide 4. Yeah, just type it in slide 4. Okay, and once you finish typing that in slide 4, we're done with that Desmos activity. Just a short, like, investigating what happens when you change A and B. And that's what happens, right? When you change B, the graph just kind of gets steeper. And then when you change A, it gets steeper. And B goes, you can't make B negative, right? B has to stay between 0 and 1. Okay, so let's go back to, so that's number 2. We wrote a little bit down for 2, but mostly you did it in Desmos. I'm going to clear out the screen and go to the next slide. Okay, I am in the next slide. This is number 3 here. Okay, discussion points. What special values of B should we consider? Are there any other values of B we should try? How many different types of graphs can we find? How do we know we have found all the possible graphs? Okay, so we got different graphs. We got some that were flipped over, right? Like this one's going down, right? But we'll talk about those later. The graph of the function y equals 1/2 to the x is shown at the right. Wait, did we go? I feel like we did not answer all the questions. Let's see, I need to go back for number 2 or number 1. Okay, so these were the graphs we got, right? So when we made B bigger, it went higher, faster, right? And so when B is smaller, it still goes high, but it's not as fast. It doesn't increase as fast. We got this when we didn't show this too much, but this is case number 3. How can we get, instead of going up, this graph is going down, right? How can we make the graph go down? So let's go back to slide 3 here. The graph of the function y equals 1/2 to the x is shown right here. So we're going to draw this and graph this, okay? So we're going to write y equals 1/2 to the x. We should have did 2 to the x. That's what we needed to do. Let's do 2 to the x. Let's back up a little bit. I got ahead of myself. Okay, because I was wondering, I was like, where do we do that? Okay, so I'm going back to number 2. Well, it won't let me go back. There we go. It won't let me stay back there. Let's do y on your paper equals 2 to the x. What we want to do is we want to make an xy table. Okay, and we want to put some values in here, like let's put -3, -2, -1, 0, 1, 2, and 3. Okay, so we'll go from -3 to +3. When we put -3 in here, okay, so if I do 2 to the -3rd power, what is that, you guys? -3rd power is not a negative number, it's a fraction. Remember, we don't like negative exponents and we always tell you to get rid of them. Well, to get rid of them, you put them underneath a 1 like that, and then you bring it to the denominator and you make it 2 to the +3rd power. That is what you do with negative exponents, okay? So with negative exponents, you get rid of them. We always get rid of them by putting them underneath a 1 and making them positive. And then 2 to the 3rd is 2 times 2 times 2, which is 8. So it's a very small fraction, 1/8. So 2 to the -3rd is 1 over 2 to the 3rd power, or 1/8, which is close to 0, right? It's a little bigger than 0, but not much. Okay, so this is 1/8. 2 to the -3rd power is 1/8. Okay, let's put 2 to the -2 power in here. Okay, 2 to the negative 2 power is 1 over 2 squared. Right? So to get rid of that negative exponent, we put it in the denominator like that. See what we did there? And 1 over 2 squared is going to be what fraction, guys? It's going to be 1/4, right? Which is slightly bigger than 1/8. It's twice as big as 1/8. Okay, so let's do the next one. All right, good. Let's do the next one. 2 to the negative 1 power. Right, so I'm putting -1 in here. 2 to the negative 1 power, that's going to be a fraction. What fraction is that going to be?
1/2.
Good, 1/2, exactly. Right, we do 1 over 2 to the first power, or 1/2, which is twice as big as 1/4. Oh, wait, this is twice as big, that's twice as big. Oh, our multiplier is 2, right? Okay, let's see if you guys know the next one. This one's kind of a tricky value. What's 2 to the 0 power? Take a guess.
1.
Okay, 1. One person says 1, and then I'm checking the chat. 1, good. 2 of you said 1. Nobody said 0. Sometimes people say 0. Some people think 2 to the 0 power is 0, but it's not. It's 1. Anything to the 0 power is 1. So 0, 1. Notice all our graphs that we did in Desmos always to pass through 0, 1. That's 1 right there, because this is going by 2s. This is 2, 4, 6, 8, 10. So all the graphs went through 0, 1. That is our y-intercept. Okay, and that's super important, is where's the y-intercept? For these problems, it's super duper important that you know that the y-intercept is at 0, 1. Okay, let's do 2 to the first power, because we're putting a 1 in next, right? That's easy, right? What's 2 to the first power? 2. What's 2 to the second power? That's pretty easy.
4.
Good. 2 times 2 is 4. How about 2 to the third power? We kind of discussed that already.
8.
It's 8, right? Because 2 to the third power, 2 times 2 is 4, and then 4 times 2 is 8. It's not 6, right? It's not 2 times 3. It is not 2 times 3. That is not what 2 to the third is. It's 2 times 2 times 2, which is 4 times 2, which is 8. So 2 to the third is 8. Okay, and we can do 2 to the fourth. What would the next one be? Look at this pattern. What would the next one be?
16.
That's right, 16. And it's going to keep doubling, right? And if you keep doubling something, it's going to go up pretty quickly. So if we make a little graph on our notes, we want to make a little graph. Let me move my little bar out of the way. Oh, that line is terrible. Let me make a better line. Let's use the line tool like this. And I'll make a better line like that. And then I'll make a line over here. And I'll go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. I could keep going. Okay, let's number this. We always want to number our graphs. So let's go by 2 since we go up pretty quickly. 2, 4, 6, 8, 10, 12, 14. I have 16 here. I could keep going. I guess I'll go by 2s here. 2. I like to keep the axes the same scale. No, I lied. Oh yeah, that's fine. Okay, so 0, 1, right, is our important point. And we should go -2. Don't ignore the negatives, -4. So we started at -3, 1/8. -3 is right here, and 1/8 is close to 0. So just right above the x-axis, right? And then let's go to -2, 1/4. So -2, 1/4 is just slightly above that. And then -1, 1/2 is higher. It's halfway. Oh no, that's 1. So I want it actually lower, like right here. And then 0, 1 is right here, like we said earlier. And then 1, 2, 1, 2 is right here. 2, 4, 3, 8. and 416. Oh, good thing I went to 16. Let me change my color to black because I have, well, let me erase this stuff right here. That'll be helpful. All right. 416 is right here. So now we can make a graph. Okay. Oh. Okay. Is this graph ever, is this gonna cross the x-axis on this side down here? Is it gonna go underneath to the negatives? Let's write this. This graph will never cross the x-axis for this graph and many others. Anytime b is, well, b is going to be between 0 and whatever. It could be, let's say b is between 0 and 10. It will never cross the x-axis as long as a is greater than 0, okay? When we say a, the equation was y equals a times b to the x, right? So right now we're just doing b to the x. Once you make a negative, right, that changes everything. That flips it over and does crazy stuff. But if we don't add anything to this equation and we just leave it like this, once we like, if I were to subtract one, then it would move it down, but that's a whole different thing we'll cover later. This will never cross this axis. We have a special name for that. That is called an asymptote. I'm going to draw the asymptote on here in red. Okay, so draw a, you know, with a different color, or maybe you would make it, I would make it dotted. We like to make our asymptotes dotted. Now I'm changing to green just so you can see it. I want to make it not just the x-axis, but I want to make an asymptote. Okay, so let's write that word. Have you guys heard that word before? Asymptote? Okay, good. Hopefully you heard it last year. Okay, especially if you took this class last year, then of course you've heard it. The asymptote is a line that the graph never crosses, and it never crosses the x-axis. The equation for the x-axis is y equals 0. Believe it or not, that sounds backwards, right? Because it's the x-axis. So shouldn't the equation be x equals 0? No, it's actually y equals 0 because all the coordinates on the x-axis have a y coordinate of 0. 2, 0, 4, 0, 6, 0, 8, 0. So we have an asymptote there. That means this graph will never cross that asymptote. It'll get closer and closer and closer and closer, right? Like this graph's gonna get closer and closer and really close, 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 but it will never cross the x-axis. And that's super important concept. You need to indicate that on your graph by two ways, by drawing the asymptote, drawing the dotted line. You always need to draw the asymptote in, and by extending the left part of your graph as close to the x-axis as you can. What you don't want to do is this. Like some people, we call this copping out. When you draw the graph and you don't commit and you just kind of go like that, and you don't show me that this graph is not going to cross the x-axis. The way you drew it looks like it's going to cross the x-axis. So you need to extend the graph all the way down to show that it's getting closer and closer, okay? Don't cop out and just do like a little curve like that and not extend it all the way, okay? So you now know what an asymptote is, and all these exponential graphs have an asymptote. There is a value that it will never cross, and it's usually the x-axis, okay? So, okay, that problem was huge right there. What we just did right there is that's how you graph all exponential functions, okay? So I need to erase this. So if you need to take a screenshot or a picture of it really quickly before I erase it, then please do so. All right, then I need to look at number 3 here. I need to go to the next slide. Move this out of the way. The graph of the function y equals 1/2 x to x. Okay, so now let's change our b value, right? So for 8-3, our general equation is y equals b to the x. Now we're going to change b to 1/2. What happens when we change it to a number less than 1? Sorry, that's supposed to be an x right there. Less than 1, make it, because this is 0.5, right? What if you make it a number between 0 and 1? What is that going to do to our graph? So It says the graph's right here. Well, let's see if we can make an XY table for this. I'm gonna have to work down here. X, Y. You know what? I need more space. I needed to go over here. X, Y. Let's put -3, -2, -1, 0, 1, 2, 3. Okay, let's put these values in and see what happens. Okay, so if I do 1/2 to the -3 power, ooh, what do you do with that? Well, when you have fractions and negative exponents, you're gonna flip over the fraction to make it 2/1, okay? It flips over the fraction. When you have a negative exponent with a fraction, you flip it over and then you put it to the 3rd power. Oh, well, 2/1 is just 2 to the 3rd power, which we know is what, guys? 8. So this is 8. So if you see a -2, 8 is, this is a different graph, but yeah, that's where this one's gonna be. Let's do 1/2 to the -2 power. So the next one is -2. That's gonna be, we're gonna flip over the fraction.
4.
Good. 2/1 squared, which is 4, because we get 2 squared. So this is 4. Now let's do 1/2 to the -1 power.
2.
Good. You're gonna flip that over and do to the 1 power, which is 2. The custodian's right outside my door, leaf blowing. It's nice. All right, I love our custodians, they're awesome. All right, so 1/2 to the 0 power is, what's anything to the 0 power,
1.
guys? Good, 1. So that's gonna be 1. Again, that's our important point. That's 0, 1. We're gonna graph this in a second. I wanna make like a graph here somewhere. And gosh, move my bar out of the way, make another line down here. And 0, 1 is gonna be right here, right? 1. So 1, 2, 3, 4, 5, 1, 2, 3. Oops, you know what? I want to go by 2s again. So I'm going to change where 0, 1 is because I actually want to go by 2s. So change my pen. 2, 4, 6, 8, 10, 12, 14, and I think we just need to go 16. All right. And then we'll make this -2, -4, -6. +2, 4, 4, 6, 8, 10. Okay, let's finish the graph, but I know 0, 1, I know my graph has to go through there. I just wanted to mark that super important point where it crosses the y-axis, very important. Then we do 1/2 to the 1 power. That's pretty easy. 1/2 to the 1 power is?
1/2. 1/2,
yay.
Yeah.
How about 1/2 to the 2nd power? What is that going to be? Whoa.
1/4.
1/4. That's right. Because you square the top and you square the bottom. You square the numerator, you get 1. Square the bottom, we got 1/4. So, and 1/2 to the 3rd, what's that going to be?
1/8.
1/8.
Yeah.
Okay, how is this related to the table that we did last time in the last problem? It's very similar to the table that we did in the last problem.
It's just the opposite, basically.
It's just reversed, right? Like the 1/8 was up here. These two are switched. These two are switched. Those two are switched. So it's just flipped around. So it's the exact same graph. So 4 should be 1/16, and we should throw -4 in here. -4 is going to be 16. So -4, 16. I'm gonna graph that first. -4, 16. Then -3, 8 is right here. Then -2, 4. -2, 4 is right here. -1, +2 is like right there where I put the 2. And then 0, 1, of course. And then 1, 1/2. 1/2 is right here because my 1 is right here. So 1/2, and then half of that, and then half of that, and then half of that. And it's just getting closer, half of that, but it will never cross half of that, half of that, half of that. It will never cross the y-axis. So the graph that we want to draw goes like, it's increasing, increasing, decreasing, decreasing. It's decreasing, 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 decreasing. More, 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 more. And I want to draw it closer and closer and closer and closer, but never crossing the x-axis. Should we draw the asymptote in, guys?
Sure.
Yes, always draw.
0.
Yep, y = 0, exactly. The equation of the asymptote is y = 0. Asymptote, that is how you spell it. Okay, y = 0 is the asymptote. All right, and we'll draw arrows at the end because it keeps going, right? It keeps going, it keeps increasing, increasing, and it keeps going this way. So always put arrows at the end of both of your graphs. So this is what y = 1/2 to the third looks like. Anytime your b is between 0 and 1, not equal to 1, because we know what happens when b = 1. That's a special case, right? What happened when we did Desmos and we let b = 1?
It was a straight line.
It was a straight line right through 1. So we'll draw that. That's why you can't let b = 1, okay? B, when you do these problems, b cannot equal 1 because it won't be a curve. It'll be a straight line. So we always say b cannot equal 1, okay? We want, if b is between 0 and 1, we're gonna get decay, which means it is gonna decrease. The graph is gonna go down. So if b is between 0 and 1, these are all decimals like 0.1, 0.2, 0.35, 0.67, 0.98, any number between 0 and 1, right? If your b value, your base, the b stands for the base. If it's between 0 and 1, your graph is gonna decrease. It's gonna go down, okay? When is it gonna go up? When is the graph? How can we make the graph go up instead?
1.
So b has to be greater than 1, okay?
Yeah.
So your base has to be greater than 1. We never want b to equal 1, because if you let b = 1, it can equal 1, but it's gonna be a straight line, right? b = 1 is a straight line going through 1. We can have that, you know, like y = 1 to the x power. Well, when you do this table, x, y, you know, if I do -3, -2, -1, 0, 1, 2, 3, I'm just going to get 1, 1, 1, 1, 1, 1, because 1 to any power is 1. Okay, so when b is greater than 1, we're going to get a growth. We call this exponential growth. It's going to grow. When b is between 0 and 1, it's going to decay. It's going to go down. When b is equal to 1, it's going to be a straight line. All right, that's the main thing that you need to learn today from today's lesson is when does it go up? When does it go down? And how to make a table and how to graph it, okay? So we learned how to do exponents a bit. And that is the main thing. All right, I gotta clear the screen away. So if you need to take a screenshot, please do so. Almost finished, we're almost done, guys. Thank you for being patient. It's the first lesson of the chapter, so we got to be kind of thorough here. We're almost done though. Part 2. Now that you, with your class, have found all the possible graphs for y = b to the x, your teacher will assign your team one or two types of graphs to investigate further. No, I'm not actually. And then you're going to make a poster. We're not going to make a poster. As a team, organize your graphs and summary statements. No, you know what? We don't need to do 4. We're good. And number 5, exponential functions have some interesting characteristics. Consider the functions of the form below. Exponential functions such as y = b to the x are defined only when b is greater than 0. Why do you think this is? Why can't b be less than 0? We didn't discuss that. So for, you know, B4, I'm sorry, 8-4, we're skipping that, right? 8-5, why can't b be less than 0? Why can't we have y = -2 to the x power and let our b be negative? Well, if you let your B be negative, you're going to get like a positive value, a negative value, a positive value, a negative value, a positive value, a negative value. And it's going to go back and forth, and it's going to go like this. And we don't really have graphs like that. Maybe this is called an oscillating graph. We do have times that we have oscillating graphs, but this oscillation is increasing, which I don't know, maybe you could have, but we just don't do that. So the B can never be graded. We're not going to do this, right? I'm going to put not possible. I mean, maybe it is possible, but we don't really use this, right? B cannot be less than 0. Not possible. Okay. For part B, I got to move my thing out of the way. I can't see it. Can you consider y equals 1 to the x or y equals 0 to be exponential functions? Why or why not? How are they different from exponential functions? So if we have y equals 1 to the x, what's going to happen when when b equals 1?
Straight line.
It's just going to be x. It's a straight line. Is that an exponential function?
Nah, no.
Why isn't exponential? There's an exponent here, so why isn't it exponential?
Because it's not growing.
Exactly. It's not a
Or
curve, right? This is
yeah.
not a curve. It's a linear graph. It's linear. So this is not considered an exponential function. How about y equals 0 to the x? I'm running out of room here. 0 to the x. Whoa, what if we do 0 to the x? Let's look at that. If you do y equals 0 to the x, x, y, -3, -2, -1, 0, 1, 2, 3. If I do 0 to the -3, 0 to the -2, 0 to the 1, 0 to the 2, 0 to the 3, what do you get when you do 0 to all these powers, guys?
It just creates 0.
Okay, these just create 0. All the positive ones make 0. But what about negative? What if I do 0 to the -3? What does that equal? Zero, 1 over 0, right? Is it okay to have 0 in the denominator?
No.
No, you're not allowed to. No, you not okay. You can't divide by 0. Okay, try it in your calculator. See what happens when you try to divide by 0. Your calculator doesn't like it. It'll give you a message.
It said domain error.
Exactly, because you can't divide by 0. So good, I'm glad one of you has your calculator out. Not okay, you can't divide by 0. So you can't even get values. So it's kind of a straight line, right? So we would have like a straight line from here on at 0, 0, 0, 0, 0, 0, right? But we wouldn't have a graph over here. There would be no graph over here because it doesn't exist, does not exist. So it would be like a flat line too, right? It would be a flat line from 0, from x is greater than equal to 0, and it would go on. But that's definitely not an exponential function. So we never let b equal 1, and we never let b equal 0. We're not going to let b equal 1 or 0. Not allowed. That's why we say b has to be greater than 0. So b has to be greater than 0 or less than 1, or b can be greater than 1. But it can't be equal to 0, can't be equal to 1. All right, guys? Okay, let me pause it there.